Here we are, it's the psci 168 video lecture. psci 168 video lecture 5. So I had a couple of questions about the height of the tree homework. So that's a good place to start. And then we'll continue on with our forces and the direction of force and the structures that we've been talking about. So let's just call this homework review, and I'll set that problem up. Wait a minute here. Okay, we'll say I have something in a moment. Okay, so the homework review problem was that we had this tree and we wanted to find its height. And originally we had h, lowercase h and L, and the height of the tree is uppercase H and uppercase L. And we had, by the law or just by the property of similar triangles, this lowercase h over L is equal to this uppercase h over L. And we just have to solve for h by cross multiplying or multiplying both sides by capital L. So what we have is h over L, this ratio, times capital L. So now what we did was we put some numbers in, and I did give you guys a trig function. I said, here's the h, here's the L, and here's the alpha. And I said alpha was 50 degrees. But the definition of the tangent of alpha, and you get this right off of a calculator, the tangent of alpha is precisely this h divided by L that we would have here. You know, we could put that alpha here as well. So for that reason, when all is said and done, so h is going to be this tangent of 50 degrees times this L. And you just go with you have a calculator, it has to have a tangent function 50 degrees, and you will find, what did I find here? Tangent of 50 degrees was 1.19. 1.19, and then the L was 30 meters. And so as my answer I had 35.75 meters. Okay. Meters. There we go. So that's the height of a tree. And you'll see, this is a good technique. This is a surveying technique. You pace off your distance from the base of the tree, figure out that L, and then you sight up at the top of the tree with some device, has a protractor built in so you can actually measure that angle. And these trigonometric functions just embody all of these triangle relations, okay? So there's nothing mysterious going on here. And all of our measurement, or a lot of our measurement of the world and the solar system, as it were, is based on these types of geometric relations. In particular, surveying is based on these types of geometric relations. Good, so there's the homework review. Next, we're going to continue on with the structures in the vector nature structure. And we had already gone through a few. I'll just kind of list them. We had post and lintel. We had Roman arch. No, we had the roof gable. We had the Roman arch, and we wanted to get some pictures of these, and we're going to move on to the Gothic arch next. So 4, we have the Gothic arch. You'll get excellent visual examples if you look up Gothic arch. The Gothic arch is a pointed arch, okay, and as a result, it has the same, we're call it problem. Namely, if you're trying to, let's make this one a little bit shorter. Let's call that the Gothic Arch right there. There is going to be an outward thrust based on the vector nature of these compressions. And so the question is, so there's going to be an outward force component, and you've got it on both sides, and it's going to tend to push your walls apart if you happen to have some tall walls of one Gothic cathedral. Okay. So what was done in the Gothic cathedrals, they wanted to have kind of a skeleton style structure where they could put big stained glass windows in. They have what are called flying buttresses that come out like this and continue to bring those forces, catch those forces here. And so I'm going to write that down for you guys as well, flying buttress. And they even have tertiary ones. That means they'll even have, some cathedrals will have a third structure down here. So you can look up your Gothic arch, your cathedral, your Gothic cathedral. You can look up the flying buttress and you get some excellent images. And what you'll see, you'll never look at these things the same way again, because especially with these cathedrals, the skeletal structure is often really apparent. And now that you know about forces and compressions, you're going to see what the principle was to have a roof over this giant inner hall here and not have the walls fall out. Okay, so you'll actually get a good view of that. So the Gothic arch and the cathedral, we keep a little list here. Gothic arch. Another really interesting structure is the Pantheon in Rome. So I want you to get some pictures of this as well. Pantheon in Rome. And the construction principle of the Pantheon is very interesting. Imagine you have a sphere, okay? And the upper half of the sphere is going to be, well, you start with a sphere, okay? Then here I'll use different colors. Then the bottom part of the Pantheon has these really thick walls, okay? Based on this sphere, the upper part, okay, so the walls are very thick. The upper part has this poured concrete shell, and in fact, the top is open. It's called the oculus. Okay. So this sphere here, we can erase, or less. And then what they did in the Pantheon in front of it, they kind of built a standard temple entrance that I can't draw very well here, with the gables and columns coming down. But the whole thing, so that's just the part that sticks out, but the rest of this thing is a gigantic hemisphere, poured concrete. We're talking about 40 meters high, like 140, 150 feet inside the diameter of this thing. Oculus is open, so instead of a keystone, they left something empty there. But now that we know about vectors and forces, one thing they did was they made the walls really thick. Okay. And then we know that these forces are going to be channeled down this way, directed. Walls are thick enough not to fall apart. So look up the Pantheon in Rome. I'll just write it right here for you, Pantheon. And got the poured concrete shell. This thing's 2,000 plus years old, 2,300 years old or something. It's a great tourist attraction. Amazing thing to see. This 2,000-year-old poured concrete that still is standing. Good, so get some information on that. You'll be pretty interested. Now I'm going to shift gears a bit, so we're actually not leaving the subject of forces and tensions. What we're going to look at next is, brought a chain to class here. We're going to look at the shape that a flexible chain is, as flexible as anything, right? We're going to look at the shape that it assumes just under gravity. This curve here has a name, and we're going to analyze it as well. Got to get okay, I had to get something out of the back there. So I just have these magnetic little pins, and this way we can analyze the shape of this chain. And by the way, everyone, if you have a chain, girls have a necklace or something, it's going to do exactly the same thing. A smaller or larger chain, it's going to take on this beautiful shape here. Now, what about the analysis of forces here? Well, the tension in this, because it's flexible, is tangent to the curve. The name of this curve is called the catenary. Okay, that's the shape that a hanging chain assumes under gravity. Chain, you know, you can have the same thing with a rope, but the rope's not necessarily dense enough to have such a smooth shape. Okay, so chain works better. Chain under gravity. And this is something that can be analyzed, really sophisticated stuff, but we just are going to be clear that the tension is always in the direction tangent to that curve. Tension is tangent to the curve. So you could never draw one as beautiful as what nature has here. Just this natural curve. And when I say tension is tangent, I mean everywhere along this curve. Here at the very top, you know, it's coming in at that angle. Everywhere along it, the tension is tangent. So I have that, and at the very bottom, the tension is horizontal. Okay, tangent to the curve all the way along it. Another interesting thing is you can have different catenary. It's still the catenary. Okay, this one looks different. What it in fact is this curve here that I have right here for you is this part of the bottom curve. It's geometrically similar. You could say it's been magnified. Okay, it's all the same curve, the catenary. So there are two very important applications of the catenary. Good. If you have these facts, I'm going to go ahead and erase and do a little application. So since we were numbering things, 6, the catenary. And let's go ahead and just hang this here. I'm going to do a little construction for you. So you get this beautiful curve, and now you imagine you wanted to build a bridge. Okay. So if you wanted to build a bridge, you would have to have towers here, and tower here. Okay. And you would have a road, and the road is right here, and what this giant suspension cable is doing, it's holding up the road. That's why you have these vertical, smaller cables. And here's the road, a little thicker. Okay, so the road comes out here. Yeah, now we know enough about tensions to realize that this bridge isn't done yet, because here we have very, very strong tensions pulling in. Okay, like that. So there must be a cable on the other side to balance those tensions. And if you look up a suspension bridge, and again, you'll find beautiful pictures that will exemplify this. That's how a suspension bridge, that's a construction principle of a suspension bridge. You have to have these cables as well coming out here to anchor it, otherwise the towers would be pulled in. So there, again, we have the vector nature of force. Of course, the simple addition, we have the towers pushing up here. Everything is balanced. But that's the catenary. My final example with the catenary is going to be if we invert the catenary. Here, I'm going to complete this drawing just because I got to use the chain some more. Okay, so there we go. Now finally, let's take this one again. It's going to be about right. And yeah, like I said, you have a little chain, you can play around with that, you'll see exactly what's going on. So suppose we took this curve in which the tensions, the tensions are perfect here, okay? They're perfectly parallel tangent to the curve itself. Suppose we invert this, suppose we make this solid and then invert it. If we do that, so make the catenary solid and invert it, we have the Gateway Arch in St. Louis. Okay, so the Gateway Arch in St. Louis, you look that up, it's, I don't know, 700 feet tall, it's huge. Look up the Gateway Arch and get some pictures. It's just an inverted catenary, that's the principle of it. It's not exactly the catenary because of the greater thickness at the bottom than the top, but it's definitely the principle. And the important principle here is that there is no buckling. It's been designed with the perfect shape to take the compressions all the way down to the ground, and so it can be made thinner than, say, a Roman arch. So yeah, now we have a bunch of interesting examples, and you guys will get some images for this. And if you have an image and you can want to draw some vectors on, fine, or you may find some images in which the arrows have been drawn in, because that's an interesting topic that's been dealt with. So let's see how we're doing time-wise. Okay, excellent. So those were the elements and the structures I wanted everybody to have a good look at. And now that we know about the directional nature of force, the vector nature of force, these things make sense. Okay. Good. So next, I'm going to formulate a couple of problems that we want to be able to solve. I'll just call this homework. These type of problems, you leave enough room in your notes and try them. And if you can't do them, just as with the one I did on the board today, send me the email that you'd like to see a certain problem done. Because that's the kind of problem we will put on the exam, like a height of a tree problem. I could put that on the exam. So this next problem is also forces and directions. And we'll do it with the roof gable. So let's call this homework problem the roof gable problem. So homework problem And what I'm going to do is draw a roof. And here are some walls of the house. And I'm going to stand up here. I'm going to weigh 900 newtons. Okay, 900 newtons. We're going to ignore the weight of these beams. We're going to say, okay, it's all my weight that is doing what? It's pressing down, it's pushing out, it's pushing these walls apart. So if we label our triangles, and since forces are like vector, like arrows, we're going to have two similar triangles. Okay. And if I'm 900 newtons, then this has 450 newtons. Okay, that's what we know about it. 450 plus 450 is 900. So let's go ahead and just isolate one of these triangles. Okay, and we have 450 newtons. Now we're going to do a similar triangle, because remember, this is just geometry. So if I take the same triangle and just discuss its geometric properties. So all I know is that this is 450 newtons, but geometrically, I'm going to say that this is 1 meter, similar to, here, let me make a little room here. Let's write a little smaller. Similar to, so this is 1 meter, and this here is, well, let's make it realistic, 1, 2, 3.5 meters. So here's what we want to do. We're going to call this X. Well, what do we call this? No, we'll just call this H. It's a hypotenuse, so apparently our Pythagorean theorem can get the hypotenuse. And having done that, we want to find this f sub x, and I'm just going to label these A and B, or A and C. So A and C are forces, and these two triangles are similar. So homework is to find H, that's in meters, and then find A in newtons, and find C in newtons. And you know, it's just geometry. And since I've kind of drawn these reasonably to scale, you can see that approximately, if this is 450, you know, this is going to be somewhat over 1,000. Okay, A is going to be over 1,000, C is going to be over 1,000. And that's the force that is pushing these walls apart. Okay, so similar triangles will get us the forces that are pushing the wall apart, will get us the force along the hypotenuse, which is the actual one, that's the actual board, okay? Good, so I'm gonna let you guys try that. Remember, similar triangles, any ratios, you can say 450 divided by A is the same as 1 meter divided by 3.5. Okay. That's simple. And you could say 450 is to C as 1 meter is to H. And each of those would be ratios. You know, 450 divided by C, 1 divided by H. So using the similar triangles properties, want to get H, want to get A, and want to get C. And then you know enough. Okay? You can solve any number of problems of that type. Good. So now we are actually moving on. I'm going to give one more law of mechanics. Well, okay, let's put it this way. we've talked about forces and vectors, directionality. We've seen that it brought us back to the geometry. So everything we've done up until now was, first of all, geometry, and then we had that force concept, which obeys the laws of geometry. Now I'm going to introduce one more law, a very simple one, because the question arises, what kind of techniques can we use to actually build these kind of structures? We've analyzed their shape and the forces, but how do we actually lift things up? How do we build things? And the concept is going to be leverage. So we're going to start with the law of the balance and then the law of the lever. And usually I spend a bunch of time demonstrating these things, so I would have slides for all these images here, interesting slides. But you guys are going to do that yourselves, print them out and put them in your book. Good. So we'll just finish this, and that'll leave you guys plenty of time to go searching for good pictures by talking about the law of the balance. So this is a new section, so to speak. Law of the chapter, you can write a chapter. The law of the balance. Balance. And I always have a ruler with me, and we're simply going to imagine, I'll do this next time, we have a string around here, and I have a balance beam, okay? If you want to build one, well, we'll do that later. Let's just talk about this actual abstract law of the balance. So you have a balance, some kind of beam here, meter stick. You go right in the center where it's going to balance. If you put a loop of string here, nail this to the wall somehow. If you put the loop of string a little bit above the center line, okay, it'll be stable. It won't tip that much, okay. Whereas if you suspend it exactly from the middle or for beneath the middle, of course, it's very unstable. Be that as it may, there's our balance, and just like the teeter-totter or something, what we're going to do is hang a weight on one side, and we'll hang a weight on the other side. And I think everybody can see well enough. Shorter and larger distance. Okay. And the law of the balance is as follows. I'm going to use the letter W for the weights. I could also use force. I could call them F. Yeah, I'm going to call them F for forces. The weight is a force. So let's just call this F1 and this F2. Now the crucial aspect of it is the distance to this axis right here, the perpendicular distance, and we'll call this L1 and L2. And what's the law of the balance? It's just that this product here, also referred to as a moment, F1 times L1 is equal to F2 times L2. So F1 times L1 is equal to F2 times L2. So you need some standard weight. Say you have a standard weight here, so and so many newtons, then this sequence of measurements will allow you to weigh any of the unknowns. Okay? But this relationship holds regardless. So example, let F1 be a standard weight, which is to say a known weight, some known weight, then F2, which is the unknown weight that you want to know, is simply solving for this. It's F1 which is known, times this ratio. We're just going to divide L1 over L2. Okay, so we've talked about these kind of divisions. You just divided both sides by L2, isolated F2. So if this is a standard weight, say a Newton, then you can know how many newtons something is. We're going to see later on that we can also do the same formula for masses, okay? But we haven't gotten to mass yet in our systematic derivation. So right now we're still just talking about forces or weights. But yeah, you can weigh things, and it could be very important. If you had a fine balance here, you could weigh, say, some fine piece of jewelry, and you could then figure out, take a couple extra steps, but you could figure out whether it's made of silver or aluminum, or gold or brass. So it could be very important. Platinum or who knows what. Okay. So that's the law of the balance. And I won't assign anything for this yet because we're going to do more examples. The next thing I'm going to do, center of mass and the law of the lever. That'll be our next topic, but for right now we have this law of the balance. One thing that would be good, but I have to bring it and demonstrate it. Let me see if it's here in my stash of things here. Actually, I have, very good. See how the time is right now. Okay, I'm going to show you one more thing, then we'll wrap it up. So for the law of the balance, what I'd like for everybody to do, and what I do when we're face to face, we actually get a plastic ruler and have some loop of string, and we make a balance. And what you'll notice is I put the hole in the ruler up towards one edge so this thing is stable. Okay, it'll come to rest as opposed to just tipping uncontrolled. Now, since we've been doing geometry, I also cut out a square and a circle out of the same sheet of cardboard, and you'll notice this circle fits exactly into this square, which means that if I have a circle of radius r, then I have a square of side 2 times r. Yeah, which one is heavier, do you think? Okay, well, looks like the square has a little more material on it, so the square is heavier. If I balance these, and of course, this can get fun. Actually, I'm going to put this right up on the board here. Law of the balance. Here, let's send this up. Yeah, this was a project that I wanted everybody to have. You'd be surprised how many people don't know the law of the balance until they learn it in this class. Nothing wrong with that. So we would suspend our balance. I could have a much bigger one for visual purposes, but here we go. We've got that balance suspended. The heavier weight is always closer to the axis than the lighter weight. That's what that relation there means. So I'm going to put the heavier weight a little bit closer than the lighter weight, and you guys could zoom in on this, or let's put this one out here. Now, because they're not that much different, it's going to be subtle, but here we go. Okay. There we have it. Okay. This one is closer, this one's a bit further away. And just to make it visually perfect, go something like that. Okay, good enough. Now, because there's a geometric ratio here, there's actually one more thing that we can say. So for this example, same cardboard, we have this F1 and this F2. We have on the left side 2r squared, the area and the weight will be proportional, times L1 is equal to pi r squared, which is the area of the circle, times L2. So there's an example. You know, if you want to build one of these, you could actually measure these lengths carefully and estimate pi, because what's going to happen is the r squared is going to cancel, so 4r squared L1 pi r squared L2, you can cancel the r squareds, and then you could actually get a measurement, you want to call it that, would just be 4 L1 over L2. And what's that going to be? It's going to be, you know, 3.1, 3.15, something like that. Good. So that is as far as we're going to take it. And next time we're going, like I said, center of mass, law of the lever, and the use of levers in construction. Good. See you guys next time.